Well, hello everyone. This is Mr. Dickey's Chemistry 152 class. Today I'm going to give you some brief examples and notes of Chapter 16 on acid-base equilibrium. As you recall, we've covered quite a bit on equilibrium, and all those same things are going to be in effect for this chapter. And just a few little differences with defining what an acid and a base is, and how that fits into our concept of equilibrium. Please don't panic if it seems to go a bit fast on the video. You can always pause, rewind, or watch over. And I'm going to be directing your attention to pages in the book. Don't try to follow along in your book just yet. Just watch and listen, and you'll be able to go back in your textbook whenever you choose. And the first page is page 651 in your textbook. I actually have this neat copy that came when I ordered a bunch of textbooks for the class. They sent one copy that was in a 3-ring binder. Turned out pretty well for these videos because it lays nice and flat. Okay, acids and bases, a brief review. An acid is a substance that, when dissolved in water, increases the concentration of hydronium or H+ ions. I'm reading from here. A base is a substance that, when dissolved in water, increases the concentration of hydroxide ions. This was first quantified by the Swedish chemist Svante Arrhenius in the 1880s. Later on, though, we developed a little better theory, Bronsted-Lowry acid-base theory. The Arrhenius definition is still valid, but they added to it. And that is that an acid is a proton donor. A proton is just another name for a hydrogen ion, H+ ion. And a base is called a proton acceptor. Any chemical that a H+ ion can attach to. So acids are giving away H+, bases are accepting the H+, often called the hydronium. Okay, here's a good diagram of how that occurs. You see the hydrogen ion attaches itself literally to a water molecule, because most all this we're going to do in water solution. Acids, bases can exist in other materials, but water's, of course, our standard medium of choice. This is the actual hydronium ion, H3O positive. 1, 2, 3 hydrogens, 1 oxygen with a positive charge. Now, the hydrogen ion, or the proton, the single H+ that you see there, is very transient. It literally just jumps from one to the other. There's no such thing as water with free hydrogen plus ions floating about independently. They all end up becoming this thing. They hijack the water molecule and they stick on, and that's where they stay. Now that red hydrogen, that third hydrogen of the hydronium ion, that's what does the work. That's what's digesting the food in your stomach, corroding the metals, bubbling away and churning away. All those things we know or characterize for acids, that third hydrogen, it's like the molecular hammer that makes that happen. And when it does, it separates and reacts chemically and leaves behind plain old water again, H2O. Down here is another example of where this occurs. Hydrochloric acid reacting with water to form a chloride and a hydronium. And the H3O+ is what dominates in solution. Notice the single-headed arrow. When these occur with a single-headed arrow, you may recall from last chapter, no equilibrium constant is necessary. It's 100% conversion. So if we put in 1 molar HCl, we get 1 molar hydronium completely. No partial ionization as we see with equilibrium systems. Now, we will see equilibrium systems with acid-base, but we'll talk about that later. Okay, here the acid is clearly hydrochloric acid. Water is acting as a Bronsted base because it's accepting the proton. Anything that accepts a proton can be defined as a base. So here even water can act as a base. Actually, water can act as an acid or a base, and we call that amphiprotic or amphoteric. Both of those mean the same thing. Amphiprotic or amphoteric means any chemical that can react as an acid or a base, depending on what it's paired with. Okay. Now here's a case where we're actually reacting the acid with another base, ammonia. HCl, the acid, and the base, ammonia. And here we're forming chloride ion. The ammonia accepts the hydrogen and becomes NH4. It gains that H positive, as you can see in the diagram. So that's a classic acid-base reaction. There's where ammonia reacts with water. Why we classify ammonia as a base. By the way, ammonia, NH3, that's the key ingredient in Windex that you may have at home. It's a very good cleaning agent. And as you can see, forms some hydroxide, which is the classic hallmark of a base. A base, according to Bronsted-Lowry, is a proton acceptor. Well, we see here that the NH3 does take a proton from water and become NH4. Water here is behaving as an acid. As we just said, it's amphoteric, amphiprotic, and is behaving both ways, depending on what we pair it with. Here we've paired it with a base, it behaves as an acid. If we pair water with an acid, then water behaves as a base. The water literally turns into hydroxide. It's stripped of one of its hydrogens and becomes an OH negative. And that extra H positive goes here and sticks onto the ammonia to form the ammonium ion. Okay, the next thing is down at the bottom here of the page, called conjugate acid-base pairs. Conjugate acid-base pairs. I'm going to try to lower the camera here so that I don't have to continue to try to hold everything. This is all kind of new for me, making these YouTube videos, so bear with me. I'm quite the amateur. I'm just trying to get the information across to you. And anyone else who wants to use these videos for any other chemistry class, you're certainly welcome. It's all public domain. Okay, a conjugate acid base is what forms on the product side as it relates to its parent. Well, here, HX, its conjugate is the X minus. And H2O's conjugate is the H3O positive. Think of it this way. The thing on the reactant side, its conjugate is what it turns into on the product side. I'll say that again. The reactant has a conjugate on the product side, and the conjugate simply is the thing it turns into. So X minus is the conjugate of HX. H3O positive is the conjugate of water. And your book has a good way of saying this all scientifically correct. One of the best ways, I couldn't understand this for a long time when I was in high school and early college days, and had a professor one time say, a conjugate differs from its parent molecule by only one H plus ion. If they're different in any other way, they're not conjugates. So if you're trying to pick out the conjugate of something, they can only differ from each other by the addition or the loss of one H positive ion. So if there's more differences than just an H plus ion, then they can't be conjugates of each other. That really helped me. Hopefully it will help you. Okay. Here's a way to an example of identifying some conjugates. You see here HNO2 and its conjugate base. It's an acid and it forms a conjugate base. Water is behaving as the base and it forms a conjugate acid. And that's always the case. Whatever the base is on the reactant side will form a conjugate acid. And whatever the acid is on the reactant side will form a conjugate base. You would never have a situation where an acid formed a conjugate acid. That's not possible. So that's always good parity to help you keep things straight when you're asked to identify these. Notice the little arrows from one to the other that you've seen me draw throughout different examples, maybe with stoichiometry. It's really useful here. Here's another example. Ammonia we identify as a base, and it forms a conjugate acid of NH4. And notice it only differs by one H positive ion. Here, we only differed by losing an H positive ion. See, we remove H positive and add H positive. So they're only different from their conjugate partner by either the removal or addition of an H plus. Great way to remember that. It's really good to, however you want to phrase that. Okay, here's a really handy chart that we'll use throughout this entire chapter. It's on page 657. It's relative strengths of select conjugate acid-base pairs. The two members of each pair are listed opposite each other in the two columns. So you see, you use it this way. Well, you can use it this way too if you're looking for strength. But what's the conjugate of HCl? It's Cl negative. What's the conjugate of NH4 positive? I can move my finger here. It's hard for me to know with the camera what you're seeing versus what I'm seeing. Sorry about that if I was getting in your way. Let me move it a little closer here. The conjugate of NH4 is NH3. And you notice each thing from its conjugate differs only by a single hydrogen, H plus ion. Hydrofluoric acid, F minus. Hydrofluoric acid is actually a weak acid, but it's one of the few substances in nature that can dissolve and attack glass. As you know, glass is very inert, and we put lots of chemicals in our chemistry glassware in our laboratory made of glass because it does not react with most things. It turns out it's not the hydrogen ion, it's the fluoride, F negative, has some special properties where it can react with glass. It's also the active ingredient in toothpaste, which attaches to our teeth. It doesn't hurt our teeth, it actually strengthens them, as you know. But that's just an oddity of HF. And the last thing here that we're going to talk about from the book today, the autoionization of water. Water is reacting with itself all the time. When there's nothing in it, when it's pure water at pH 7, which we would consider neutral, neither acid nor base, it's sitting there doing this. One water, exactly like another, they swap a proton and they form these. Now this happens to a very small degree at any given time. It was like 99.9% of the water is in water form. You know, much, much less, maybe 1,000th or 1,000,000th of a percent of the water actually does this. But this is enough. This is enough to do what we see water doing. Well, H3O positive, that's an acid ion, as would come from an acid. That's why water can corrode and rust metal. It's got some natural acid that it creates itself. Hydroxide does other chemical reactions, but it does not harm metal. So you've known since you were very small that water will rust metals even when nothing's dissolved in the water. Well, here's why. It's making some acid ions all the time, and they will attack the metal. These plain old H2O liquids, they don't rust metal. They're harmless. They're neutral. They cannot attack the metal. The H3O positive, though, can. Here's a more pictorial version where you see they're tracking with red the hydrogen that moves. This hydrogen will leave this water, go to here, leaving this as the conjugate of this one. Hydroxide now forms. This one now becomes hydronium, H3O positive, because a H plus ion simply moved. It's called the autoionization of water, also called the self-ionization of water. You'll hear me use that term, even though it's not in this book, because that's what I've heard through the years. Most other references call it the self-ionization of water.